Tardes. Si les parece, vamos a empezar con la conferencia magistral, el último evento del día de hoy. Es un gusto para mí poderles presentar, presentarles al doctor Eric Borguet, que nos va a dar una conferencia magistral, cuyo título es Single Molecule Switching and Sensing. Me voy a permitir hacer una breve introducción del doctor, profesor Borguet, quien es profesor de química en el Temple University en Filadelfia, en los Estados Unidos. El doctor Eric nació en Dublín, en Irlanda, donde se formó, pasó sus primeros años de formación. Más tarde asistió a la Universidad de París Sur en Francia, donde estudió química y física. Después viajó a Filadelfia, Pensilvania, en los Estados Unidos, y allí es donde obtuvo su doctorado en química física también, en la Universidad de Pensilvania en 1993, bajo la asesoría del profesor Hai Lung Dai. En su trabajo de investigó la absorción y la interacción intermolecular en superficies metálicas escalonadas. Su formación postdoctoral la hizo en la Universidad de Columbia, en los Estados Unidos, con el profesor Kenneth Eisenthal, utilizando óptica no lineal para investigar la espectroscopía y la dinámica ultrarrápida en interfaces líquidas. Los procesos químicos y físicos en superficie son el tema principal de su programa de investigación en la Universidad de Temple. Vamos a ver de qué es su trabajo y les comento que sus actividades de investigación han resultado en más de 150 publicaciones científicas, más de 280 charlas invitadas y más de 250 presentaciones que ha hecho. El doctor Eric ha sido mentor de 27 estudiantes de posgrado, 20 de los cuales son estudiantes de nivel doctorado, mismos que están haciendo estancias postdoctorales o carreras académicas e industriales en diferentes lugares. Ha asesorado a más de 90 investigadores de pregrado en licenciatura, muchos de los cuales han continuado estudios de posgrado también, y su grupo ha sido receptor de más de 3 estudiantes graduados o de posgrado visitantes, así como de 5 académicos en sabáticos, y ha supervisado la formación de 17 estancias postdoctorales. Es un gusto entonces tener aquí en el Congreso de la Sociedad al doctor Eric. Le damos la bienvenida, por favor.
Okay. Bueno, muchas gracias por la introducción. Es un placer para mí de estar aquí y quiero decir muchas gracias a los organizadores de esta conferencia por su trabajo y su atención, y también por mi colega, la doctora Rocío Aguilar de la UAP, que me invitó aquí. Pero disculpa, sería mejor que continúe en inglés porque mi español no es bastante. So I'm going to tell you a little bit about the work that we've been doing over the past decade or so, looking at the electrical properties of single molecules. I'm going to describe the techniques that we have used and the new information that we have discovered. Yes. Okay. So, right. So first of all, let me introduce myself. Geographically, I'm from Philadelphia, which is essentially located between New York and Washington, D.C., one of US's major cities. Our university is an urban university. We're very close to the center of Philadelphia, not quite as large as BUAP, but about 40,000 students. And over the past 2 decades, there's been a substantial investment in the basic sciences. I'd like to say also that thanks to Dr. Rusia, I've been able to meet with people from chemistry and physics and international relations here, because we do have a strong international focus. We are interested in increasing our interactions with, what is our nearest southern neighbor. My research, as mentioned in the introduction, focuses on processes at surfaces and interfaces. So that ranges from using ultra-fast lasers in a nonlinear optical spectroscopy to study water at interfaces. We do something which is a little bit unusual for chemistry groups. We actually build ultrafast lasers, producing some of the shortest ultrafast IR pulses in the world. We also have a lot of interest in porous materials. Why? Because they have huge surface areas. But the work I'm going to tell you about essentially grew out of our interest in electrochemical STM. And one of the things that I'm proudest of in that area has been our ability to follow redox processes at the single molecule level. And while I won't tell you about that, I do want to, in detail, I do want to show this image here, which shows an ordered structure of porphyrins on a gold electrode, where all the molecules are little squares, they're porphyrin molecules, and they all appear to be bright. And under the application of a short potential pulse that brings the electrode to an oxidizing potential for a short period of time, we transform a fraction of those molecules. And the dark spots we actually show are associated with reduced molecules. So this shows the power of electrochemical STM to follow redox chemistry at the single molecule level. But over the past decade or so, we have been using the scanning tunneling microscope to look at the electrical properties of single molecules. And that's what I'm going to focus on. I'd like to acknowledge, of course, my graduate students, the current team here, also undergraduates who play a very important role in our research, as well as the funding agencies without whom we would really not be able to do research, because as you all know, research is expensive. So our single molecule work started off basically trying to address the question of how well do molecules conduct electricity, and what are the laws that govern that electrical conductivity. All of you are probably familiar with Ohm's law and have probably measured the electrical resistance of metal wires. And you have learned, for example, that the resistance increases linearly with the length of the wire, and also the resistance reduces as you increase the diameter of the wire. And so important lessons are learned. The question is, do these rules apply to molecules? And at that nanometer scale, what are the rules that govern electrical conductivity? And what you'll see there is that one of the important factors is how we connect molecules to electrodes. Some of the molecules that we look at are very simple, but many of them are very complicated. And it's not always straightforward to determine what are the pathways of charge transport in these molecules. And that's another question that we've been able to look at. Being able to switch the electrical conductivity is useful if we wanted to consider moving into the realm of devices or other practical applications. And I will show you an example of an electrochemical and a chemically driven switch. I'll also show you how we can use this technique to explore the properties of new materials, even materials perhaps that do not exist in extended samples. And the most recent finding that we have is the ability to probe the electrical conductivity of molecules along different directions or different axes. So let me start off with the issue of charge transport in molecular wires. This has a long history, and essentially it is in the area of what I would call molecular electronics. Some people would point to this seminal paper by Ratner and Everam examining computational or theoretical point of view, the possibility that molecules could function as diodes, or essentially unidirectional conductors. Though you can actually find earlier examples that point to the use of molecules in electronic devices. And so if we want to have molecules as part of electronic devices, one needs to think about molecular switches, rectifiers, wires, lots of different molecular components. Why would one want to consider molecules in electronic devices? Surely silicon is doing wonderfully and is powering all of our computers. Well, as you know, our computers are becoming more and more sophisticated, And in large part, that is because we are increasing the number of transistors that we have on a computer chip. But in order to fit more and more transistors on a computer chip, we also need to reduce the length scale of these. And so we are now approaching length scales that are comparable to those of molecules. And so considering molecules as possible components is certainly not unreasonable, though perhaps not as practical as some might suggest. Well, practicality hasn't prevented very talented scientists such as Fraser Stoddart and Jim Heath from actually designing molecular electronic memories. And this is an example of one where essentially they are shuttling electrochemically through electrochemical action and creating a molecular storage device. So, good, okay. Though my computer died. So let's start from a very simple point of view. We actually want to determine the conductance of a single molecule. Now, this is an easy question to ask, but not an easy question to answer. Why? Because we need to be able to address certain challenges. First of all, we need to be able to reliably wire the molecule to the metal electrodes through which we are going to measure the current. Secondly, we need to recognize that the conductivity of the molecule depends not only on the intrinsic properties of the molecule, but also on those of the electrodes, and ultimately the entire junction that is formed by the molecule and the electrodes. One has to recognize that in spite of the pretty cartoons that I might show you, we might not always be certain about the geometry of the molecules in these junctions, nor even the binding sites to which they are determined. So there are a lot of unknowns, but in spite of this, I would say working together, experimentalists and theoretical scientists have made a lot of progress in this area. So let me tell you about how we started in this field. So we were interested in understanding what limits molecular conductance. For example, the problem of the contact between the molecule and the electrode. So essentially, one needs to have anchoring or linking groups to connect the molecules to these electrodes. And so the resistance could be a sum of the resistance of the anchoring group plus the resistance of the two anchoring groups, or more, the molecular core, but of course also the electrode materials and the coupling between all of these. And as I'll show you, connections are important in determining the resistance of a molecular junction. So this is not a field that I was interested in, negative interest, perhaps even an aversion to this. But the postdoc, research scientist who actually had shown who had done the experiments that showed the single molecule, enables to do single molecule redox with the STM, was very interested in this. And he put the question very simply by recognizing that at the time, most people were focused on using carbon, sulfur, gold bonds. They were essentially exploiting very convenient thiol chemistry to bind molecules to gold electrodes. Now, while this is convenient, and there's no guarantee that this actually forms the best electrical contact. And he actually suggested that maybe a contact that would involve two sulfurs, if you want two pathways, but also some conjugation, might be a superior contact. Now, this molecule is commercially available. This one was not, and this was one of the few times where my group engaged in actual synthesis, purification, characterization, and ultimately insertion of these molecules that have sulfur, carbodithioates, essentially a carboxylic acid with sulfurs instead of oxygens, and inserted them into a self-assembled monolayer of insulating molecules, molecules that would not conduct electricity. We showed that these molecules were well dispersed. We were able to attach gold nanoparticles to the other end. And because we were actually not involved in the measurement of single molecule properties, we actually collaborated with a group that did current sensing AFM. And this is the only current sensing AFM result I will show you. But the result is pretty straightforward. It's probably a little difficult for you to see this here, but this curve here shows the data from this molecule here, and this curve here shows the data from this molecule here. And it should be apparent to you that at a given bias, this molecule here, which has the same core as this molecule here, but different anchoring groups, conducts more electricity, and so should have a lower resistance or a higher conductance. Those of you looking carefully probably recognize that this molecule here is shorter than this molecule here because there is an additional carbon-carbon bond on each side of this. And as you remember from Ohm's law, the longer the conductor, the higher its resistance should be. So it's even more surprising that this somewhat longer molecule should show more conductivity. So frankly, I was pretty impressed that Yufan's prediction worked out, and so were my students. And before you knew it, we were using our scanning tunneling microscope and a technique developed by the late Nanjin Tao to begin to make electrical measurements. We had a fair amount of experience with electrochemical STM, being able to look at the ordered structures and phase transitions and other properties of molecules. And so we exploited this to bring essentially the STM tip, probably shown better here, into repeated contact with the surface and to measure current versus distance curves. Now, in the absence of molecules or atoms bridging the gap between the sharp metal tip and the conducting metal substrate, there is an exponential decay of current versus distance because of quantum mechanical tunneling. However, if the metal tip does actually make mechanical contact with the electrode, you can actually form atomic wires. And as you pull the tip out, you see, rather than exponential decay in current, you see steps in the current as you break the atomic wires that are formed. And this can be very repeatedly done and has a relatively high quantized conductance. In fact, the quantum of conductance we call G0 here will be a unit that we will use repeatedly throughout this talk. However, if molecules bridge the gap between the tip and the substrate, one can also see steps in the current. These are steps where even though one is extending the tip substrate distance, there is no change in the conductivity because essentially the wire or the molecule is essentially adapting and maintaining a contact. But eventually, the distance becomes too long and the junction breaks. Now, you might wonder, why are we showing an image of somebody fishing in the dark? Well, this is what my students think of this kind of experiment. Essentially, now remember, when you go fishing, you have great hope, okay? You have great hope that you will actually catch something. And so what we're repeatedly doing is we are casting our rod into the dark, knowing that there are fish there because we've put molecules in solution, but hoping that we will actually catch them. And if we catch enough, we can feed ourselves or our stomachs or our brains, depending on whether it's intellectual or other information that we want. So Yufan's success on these two molecules and the coincidence that one of my colleagues at the University of Pennsylvania had made a series of molecules that had both carbodithioates. Actually, I'll show you the series here. These are molecules with thiols and carbodithioates that have highly conjugated and therefore hopefully quite conductive cores. This enables us to test this theory as to whether the thiol is, the carbodithioate is a better anchoring group than the thiol. We used Nanjin Tao's technique. We measured thousands of current versus distance curves, did the statistical analysis of these curves, and saw peaks associated with, as we interpret, the presence of one molecule or two molecules trapped in the junction. And by repeating this measurement as a function of bias between the STM tip and the substrate, we're able to evaluate the conductance of the molecule. And so what we did here was to choose a few molecules that had already been investigated in the thiol group and compare those with the carbodithioate. So for illustration here, I'd like you to focus on this trimer here. And as you can see, you go from essentially 10 to the minus 4 G0 units with thiols to 10 to the minus 3 G0 units with carbodithioate, essentially an order of magnitude improvement in the conductance. And this again highlights the idea that contacts are very important in this. So have certainly contributed to this area. We're not alone. And I would say that there are quite a range of anchoring groups or molecular contacts that are available. And you'll see some of these in my talk. So there are many interesting and complex molecules whose electrical properties could be of interest for the kind of switching and sensing that we are seeking. Porphyrins are one such class of molecules, but they do present a certain challenge. And one of the challenges is that it is not clear what kind of junction a porphyrin molecule is going to form between an STM tip and a substrate. It's possible that the contact could be formed in the case of this tetrapyridyl metal-free porphyrin between the furthest anchoring groups here, or it could be between two adjacent groups. And the question would be whether both junctions could form, whether they would have similar or different electrical conductivity, and whether we could actually detect these. The answer is yes to all of these questions. And so let me take you through that. So whenever we want to investigate a new molecular species, it's not always clear that we can detect the molecular conductance features. And so here you have examples of current versus distance curves where there is no molecule in the junction, apparently no. So folks, hopefully I'm plugged in and I have power up there. Okay, we're back. This is an example of curves where there is basically steps associated with single molecules or multiple molecules trapped in the junction. And so statistical analysis of these curves leads to a very nice peak for at about 2 nanoamps for this particular bias. So clearly, it appears that we can measure the electrical conductivity of this molecule, and there appears to be only one value of the electrical conductance. It could be that these different pathways have different conductivities, or that only one of these pathways forms. How do we resolve this question? Well, fortunately, we were able to identify related molecules where 2 of the pyridyl groups were exchanged for phenyl groups. One would not expect the phenyl groups to complex successfully with a methyl. And so we actually were able to locate 2 isomers, one with the pyridyl groups at the furthest ends or in the 515 position, and here in the 2 adjacent positions or the 510. Now the distance here is about 15 angstroms, here it's about 10. And so there's a substantial difference in distance. And we were able to detect the single molecule conductance of both these species. And you can see that the current flow or conductivity is quite different. This longer distance has a lower current than this shorter distance. So they're clearly distinguishable. In fact, we can use the electrical measurement to distinguish between the 2 isomers, but we can also resolve the question of which is the most probable junction and charge transport pathway. And in fact, it is between the 2 most distant groups in this particular molecule. Now, in addition to investigating the electrochemical properties of the electrochemical STM of molecules and their electrical properties, part of our group was interested in carbon materials. Most of you here don't realize that when I was growing up, there were only really 2 forms of carbon. It was either graphite or diamond. Nowadays, you realize there are things like fullerenes, which were discovered in the 80s, and then in the late 80s, early 90s, carbon nanotubes became important. And more recently, people have shown the ability to create single layers of graphite, essentially graphene. Now, graphene has very interesting electrical properties. And of course, as one looks at the evolution of these carbon materials, one also asks the question, what is going to be the next generation of carbon materials? And I'd like to suggest to you that this molecule here, graphene, or this material here, graphene, could be the next generation. you can see that this system here maintains the hexagonal structure, but instead of having 6 atoms in each carbon ring as the graphene does, there are actually 18 atoms. Why? Because each side of the graphene ring has an extra carbon-carbon bond inserted into it. And so now we go from a system that has just sp2 carbon to a system that has sp2 and sp carbon. So clearly quite different structural and electronic properties. In order to investigate a material, you typically have to have access to the material. Now that has never stopped computational scientists from investigating materials. Like they can do a lot of things without having the material at all. And their calculations suggested electronic properties even more amazing than that of graphene. So if that's not enough motivation for you to go and study this, I don't know what we can do. Now, how do we resolve the problem that we want to study a material that we don't have? Well, one of the answers is to collaborate with very talented synthetic chemists who can make molecular fragments of these materials, where we can learn information about the fragments and perhaps extrapolate to the extended material. And some colleagues in Toulouse in France had made molecules with a closed ring and an open ring for this graphene-like molecule, and conveniently had very nice anilino groups that could serve as anchors. So we showed that we could actually measure the electrical conductivity of this. The dark line here is measured in solution without the molecule. And in solution with the molecule, we can see a nice peak, which corresponds to a conductivity of about 100 nanosiemens. If one takes the open ring form, here shown in its all extended format, the conductivity is significantly lower, about a factor of 30 lower. So how does this compare? Well, clearly the closed ring has much higher conductivity. It's about 20 angstroms long. Well, if it's better than graphene, let's try and compare to graphene. Well, fortunately, people had investigated the single molecule conductivity of graphene-like fragments. And they'd shown that this smaller fragment, only about 14 angstroms long, had about an order of magnitude lower conductivity than the graphene. So clearly a better conductor. But conductors are not the only things that go into electrical devices. And so we wanted to see whether we could induce any switching behavior. And so we made measurements in ionic liquid in order to have a wide potential window. And so essentially borrowing from the field of semiconductor devices, we essentially have a source, a drain, and a gate. Or essentially, from an electrochemical point of view, we can control the potential of the STM tip and the substrate with respect to a reference electrode. And by making these measurements under potential control at different potentials, one can see the peak in the conductivity shift. And so what we have happening here is that as we go to more and more negative potential, we go from our initial 100 nanosiemen value up to about 2,000 nanosiemens. And so what we're showing here essentially is some switching or gating behavior. Now, this is only a factor of 20, so I don't think Intel is going to drop silicon and take on graphene, but it does show interesting device performance. But from a fundamental point of view, it also tells us something very interesting, and I'll come back to that in a little bit. It shows that we actually have a LUMO, or lowest unoccupied molecular orbital mediated conductivity. Okay, how can we use what we've learned here to develop electrochemical switches, for example? So we had some colleagues in Switzerland who approached us with this very interesting redox active molecule. And the molecule that they gave us initially had thiol anchoring groups. Why? Well, that's what everybody does. And we looked at the electrochemical, the conductivity of this molecule as a function of the electrode potential, and saw a small modulation in the conductivity. And we hypothesized, based on our previous work, that part of the reason was that they were using a rather resistive anchoring group. And so we suggested that they actually make the molecule with the carbodithioate. And indeed they did. And so a number of things happened. First of all, they had a much more conductive molecule. And because the resistance here was far less, we were able to see the modulation due to the redox activity of this much more clearly. So conductivity is not only important in molecular wires, but it's also important in molecular switches. Another example of switching here is given by a chemical switch. Now, we're interested in seeing modulations in the electrical conductivity of molecules. The modulation of electrical conductivity suggests that the electronic properties of the molecule should change. And we want to induce this via a chemical perturbation. So when one thinks about chemical perturbations changing the electronic properties of molecules and how one might detect that, one realizes that changes in the electronic properties of molecules are often indicated by changes in color of the solution. And so when you put all these things together, it doesn't take a long time for you to start thinking of acid-base indicator dyes. And so these molecules here, which are triphenylmethanes, tend to be colored in acidic environment, but if you go to a basic environment, the solutions become transparent. Why is that? Well, as this equilibrium here shows, you change the central sp2 carbon to a central sp3 carbon. So why should that change the color? Well, if you remember from your physical chemistry, quantum mechanics, the example of the particle in a box, you remember that the bigger the box, the closer the energy levels are. And so the box here is the range over which electrons can essentially delocalize. And this alternating pattern of single, double, single bonds enables molecules in the HOMO to delocalize in the pi electron system, to delocalize essentially over the entire system. However, when one introduces an sp3 group here, the molecules are constrained to reside on the anilino groups. And so that's the origin of the color change. So we made single molecule measurements on this, showed about 70 nanosiemens in slightly acidic environment. And when we went to a basic environment, the conductivity dropped by about a factor of 100, a very large difference. And we'll explain that in a bit. Now, there are a couple of reasons why the conductivity could have changed. It could have been that we had, much more conductivity with this species here than with that one. So we looked at another triphenylmethane where there would only be 2 points of contact. This is malachite green. The previous one was pyrosanilline. And again, we go from about 75 nanosiemens to about 0.7 nanosiemens. Again, a very large effect. How do we understand this? Well, I think often when you want to understand something, you reach out to some computational colleagues. They were able to look at, in a solution-free environment, so there are some limitations to their calculations, the molecule with the central sp2 or central sp3 carbon, essentially what I would call the conjugated and the unconjugated form. And what they showed us was that the HOMO-LUMO gap changed as you move from a central sp2 to a central sp3 carbon. We knew that. That was the origin of the color change. So thank you very much. But they did actually tell us something that we could not have figured out otherwise. And that was the position of these orbitals relative to the Fermi level of the metal electrode. And in this case here, with the central sp2 carbon, the LUMO, the lowest unoccupied molecular orbital, actually straddles the Fermi level, or the level of the highest occupied electrons in the metal. And that as we go to the central sp3 carbon, it's the LUMO, not the HOMO, that shifts away. And so the change in conductivity is really due to the electron transport through the LUMO. So the molecules that I've shown you are kind of increasingly complex, and you also realize that they are anisotropic objects. And yet every time I mention the conductivity, I only give you one number, and that's a little disappointing. The other thing that one can see in these measurements is that I'm only measuring molecules, the electrical properties of molecules that have anchoring groups, and yet there are many molecules that wouldn't have convenient anchoring groups whose properties we might want to measure. So this is a story which is hopefully a motivation for students, and it's really about the importance of control experiments. Control experiments, as all scientists know, are important and necessary, but as those of us who perform them, realize they're also often boring. And they're often boring because we know the result ahead of time. But that's not always true. Sometimes a controlled experiment does not work out the way you anticipate, and that usually leads to some interesting findings. And so in this case here, the student was testing the STM tips that she had made in a solution of mesethylene, and she noticed repeatedly a peak at about 10% of the gold-gold contact. This is what we call an artifact. It's something which appears repeatedly that we don't understand, and frankly, we wish would go away. Well, she was actually persistent, and she wanted to understand what this artifact was due to. Initially, we assumed it was an impurity. She did a number of tests showing that this was actually associated with a molecular feature. And then she did something which I think was really important and you might say obvious, is she said, well, I'm making these measurements with an STM. Why don't I image the surface and see what I'm seeing? And surprisingly, and I'll show you the structure of mesethylene for those of you not familiar with it, like me, and it forms nice ordered patterns. These images are taken after the single molecule conductivity measurements, and you can see holes, in some cases as small as single molecules, suggestive perhaps, though there's no clear evidence, that the STM tip is actually pulling molecules out of the structure. And so what we have here essentially is a case where this molecule, mesethylene, frequently used as a solvent in these kind of measurements. Why? Because it has no anchoring groups and should not interfere with the measurements, forms nice ordered structures. This is not my #1 candidate for this. I'm sure Dr. Rosillo would not use this molecule to form nice self-assembled monolayers, and yet it does. It was very surprising. And the other thing is that the distance between the molecules is suggestive of the molecule lying flat on the surface. And so that means that when the STM tip comes to the surface, it approaches perpendicular to the molecular plane. And so the junction is rather short, and therefore the conductance is rather high. We showed that molecules that did not form nice ordered structures did not have the single G0. And so through this mesethylene example, we showed that we could measure conductivity perpendicular to the molecular plane at room temperature, and we could measure the electrical properties of molecules that did not have anchoring groups. And so this leads to a few questions. Can we measure the electrical properties of molecules that do have anchoring groups without interference from those anchoring groups? And can we potentially measure the electrical conductance of molecules along different axes? So we like simple molecules. I have to say my favorite collaborator is Aldrich. I'll tell you why later. But terphtalic acid is a molecule that has been well studied, and it forms very nice ordered structures under certain potential conditions on electrodes. Now, we're always interested, of course, in perturbing things, and so we thought that putting in some fluorine groups would really provide a very large electronic perturbation to this structure. And we set about trying to find out whether we could measure the conductivity of this molecule perpendicular to the molecular plane. So I know there's a lot of data here, but here we have the measurements for terphtalic acid and the tetrafluoroterphtalic acid. We see very nice, clear peaks, significantly larger than mesethylene. Mesethylene was about 0.12, 1.13. This is almost double that. So this clearly the carboxylic acid groups are having an important impact on this. But rather disappointingly, there's no difference between the fluorinated and the unfluorinated form. We see nice ordered structures under electrochemical control at negative potentials, where essentially the surface is nominally negatively charged. If we go to positive potentials, these ordered structures disappear, and the nice sharp peak that we have also disappears, suggestive of a switching behavior, because this is actually reversible. So fortunately, our theory colleagues were able to help us out. But before we did that, we actually did something else, is we made measurements as a function of the electrode potential. And what we found is that as we made the electrode potential more and more negative, what we found is that the conductance increased. Now, when you make the electrode potential more and more negative, you can think about this as injecting electrons into the electrode, or essentially moving the Fermi level up. And so you're moving the Fermi level towards the LUMO and away from the HOMO. And if the conductivity is increasing as you move electrons towards the LUMO, that suggests the LUMO is important in the charge transport pathway. So our computational colleagues made simulations, and they explained to us why, even though under certain conditions, the fluorinated and the non-fluorinated terephthalic acid would have different conductivity, under the conditions where we measured it, near the Fermi level, there essentially is degeneracy between the electrical conductivity of these two proper molecules. And they also showed that there was a huge difference between flat and vertically oriented molecules. So there we decided, well, let's take a molecular species and try to investigate its electrical conductivity in different orientations. And here we used trimesic acid, and we knew from previous measurements that this had a nice reversible phase transition from a vertical to a flat orientation as a function of potential. And so we exploited that here. Here at negative electrode potentials, we see a nice peak, possibly two peaks here, associated with nice ordered structure from the STM under electrochemical conditions. As we go to positive potentials, we have a very different pattern emerging. And based on the imaging and the IR results from previous people, we know that we should have a vertical orientation of this molecule. And we no longer have a peak in this current regime, but we have to go to significantly lower conductance to see that. And so we see a flat, that the flat conductance is about 400 times larger than the vertical. And so if we can use the electrode potential to change the orientation of the molecule, then in principle, we have an electromechanical switch. And depending on the orientation of the molecule in the junction, it will have a different conductance. Again, our theory colleagues helped to confirm this, and that was very satisfying. So I'd like to summarize here, and hopefully by telling you a story a little bit different from what you are used to doing, that it is possible with the right tools and experimental situations to measure the electrical properties of single molecules. Contacts are very important. It's essentially in determining the electrical conductivity of the overall junction. Even complicated situations where there may be multiple charge transports can be resolved with appropriate strategies. One can use this technique to investigate materials which may not exist at all. And one can have chemical and electrochemical switching. One can control the orientation of molecules in junctions, even measure the electrical properties of molecules that do not have anchoring groups, and ultimately access the anisotropy of the molecular conductance or the molecular conductance along different directions. And so with that, I thank you all. Gracias por su atención, and I will take any questions you have.
Very nice presentation, a lot of information, of course. But my question is, what will happen with conductance in higher potentials? Well, I mean, anodic potentials.
So most of the examples I showed you, we chose an electrochemical window where there was no redox activity. And essentially we were driving, for example, phase transitions or gating. But we also showed examples where one actually goes through a redox state. Now, the point about oxidized and reduced molecules is that they have different electronic structures. And so they represent a different barrier or conductance in the electrode. And so it's not always clear whether the oxidized or the reduced form is going to have the better conductance.
Nice, beautiful experiments, Eric. Thank you very much. But I was just looking at your data. For me, I was wondering, since the tip is so close to the surface, we would expect to have very high electric field. And I saw the potential were very high, even 1 volt and 1 volt. And I would expect that with that such a great field, that the surface of even the underlying material to be just blow up, as you showed before. So,
Okay, so
this is a worry.
there are different kinds of fields present here. There's clearly the electrode or the double layer potential, and that is controlled by the potential of the electrode relative to a reference electrode. We usually choose that potential to be such that we bias the surface somewhat positively or negatively. We did go to plus or minus one volt in the case of the ionic liquid, but most of the time the potential there is the surface charging is not that high. The second electric field that one needs to be concerned about is the field between that is a result of the potential drop between the electrode and the STM tip. And there again, we try to operate under relatively low bias conditions, but you still have a potential drop of a few tens of millivolts over a few angstroms. And so yes, the fields can be very strong and probably have an influence in the measurements.
And I wonder, you have calculated the current density. We are thinking that these molecules acting like a wire connecting both the tip and the surface.
No.
And
But
had you made any calculation about what will be the current density along these molecules?
The current densities can be very high. I mean, we're having essentially nanoamps of current passing through nanometer squared electrical contacts.
Yeah, it should be really, really high.
Yeah.
And the last one is, how you look at the molecules that may act as a diode?
So we have not looked at, so the question was whether we've looked at molecules that have function as diodes or essentially as unidirectional things. We have not looked at such molecules in large part because it also depends on the orientation of the molecule. So depending on, it's an interesting area. It's just not one we have focused on.
Okay, thank you, Eric.
Muy bien, ¿alguna otra pregunta?
Very nice work.
Thank you.
It's very nice because you can see the properties of the one molecule.
Yeah.
The electric properties
Yes.
of the one organic molecules. It's very nice. A very didactic your talk. Nice. Okay, how do you control? Because as you say, it's very important the resistance between the tip, the gold tip, the molecule, and the surface. How do you control the properties of the gold tip in order to make the producibility to identify the only responsible of the conductance is the molecule?
Okay, so first of all, we carry out, well, there are a number of things. First of all, we prepare the tip such that it is very sharp and we can actually image the surface. That's our first test. And secondly, we make sure that we can get the gold contacts, which are illustrative of monoatomic gold wires. The other thing that we do is we do control experiments in the solvent alone and show that the measure that we, for example, typically do not have any signatures of molecular conductivity. And that's why mesethylene was frequently used as a solvent, though people did not really look in that high electrical current range. And sometimes we do get multiple molecules in a junction, and that shows up as multiple peaks. I think, to be honest and straightforward, one of the things that, it's easy to draw pictures, and the pictures are basically our inference of what the structure is. It's based on computational results. But one of the frontiers, I think, in this area is to combine these kind of electrical measurements with spectroscopic measurements. And there are people who are basically combining these single molecule measurements with Raman measurements, because essentially you have a plasmonic structure in principle at the surface. And so you can actually measure this. But those are very challenging experiments, and a few have been done. But that's certainly an area to grow in. And it's a question that we have to keep asking ourselves.
Muy bien. ¿Alguna otra pregunta? Bueno, pues démosle las gracias nuevamente al doctor Eric Borguet. Vamos a darle también un reconocimiento de parte de la rectora, la doctora Lilia Cedillo Ramírez, y de la Sociedad Mexicana de Electroquímica. This is the present from the university. This is the one from the Mexican Society. And I'll give you your diploma later. Okay. Very nice.